In the previous lecture, we defined the notion of a computable function, which through the Church-Turing thesis was tied to computability on a Turing machine. And towards the end, we asked the question, does there exist a non-computable function? And we will answer this question in this lecture. And the non-computable function will arise from a specific problem that is tied to Turing machines, namely the halting problem. So the basic question is, does there exist a function from the natural numbers to the natural numbers which is not computable? Or related, we could ask for a set, a subset of the natural numbers, which is not decidable. And this question is rather easy to answer. The answer is yes, and we can do so by a simple counting argument. Namely, we observe that there are only countably many Turing machines. If you recall, a Turing machine is in the end just a finite list of instructions that give us the transition function. If those are fixed, then the behavior of the Turing machine is completely determined. Now each instruction is just a 5-tuple p, x, y, d, q, where p is an element of the state set, as is q. X and y are elements of the alphabet, which we assume to be finite, and in all our definitions was assumed to be binary, so 0, 1. And this is left, right, or stay. Actually, this if you think about it long enough, you'll realize that we don't even need this instruction, stay where you are. So it's kind of superfluous, but sometimes it makes programming a little bit easier. But these here, Q, A, the directions, are all finite sets. So that means once we fix Q and A, there are only finitely many Turing machines, because there are only finitely many possibilities. We can combine these elements here into a 5-tuple. And there are countably many choices, so only countably many choices for Q, right? Because we assume it's a finite state set. And we just assume that the states are always numbered, or given by the numbers 1 through n. So there's countably many choices for Q. We assume that A is the binary alphabet, finitely many onlys, finitely many directions. And that gives us a countable union of finitely many Turing machines with that particular state set. So that's a countable set. So again, the important thing is that a Turing machine is a finite list of instructions, and each instruction is a finite tuple, and the entries in the tuple are taken from finite sets. So all these sets are finite. And the state set is, for the state set, we have only countably many choices. So we have countable unions of finite sets, which is a countable set. So we have that the number of Turing machines is countable, and this stands against the fact that the number of functions f from n to n, or the number of sets as the number of sets, subsets of n, is uncountable. And that follows easily from the usual proof that, for instance, the reals are uncountable. That is the counter-diagonal method. So we have countably many Turing machines versus uncountably many functions. So there must be functions that are not computable. while this answer is rather easy, it is also somewhat unsatisfactory, because it doesn't give us an example of an uncomputable or non-computable set or function. And we would actually like to see one. So what does a non-computable function actually look like? The problem is, of course, that most of the functions we can easily write down, like f of x is equal to 2x, or f of x is equal to even more complicated things like the x digit of pi, or so on. All these functions are computable. So it's actually not that easy to expose a non-computable function, because our way of building functions seems to be made to be captured by the notion of computability. And one can make this actually very precise. There's this notion of the recursive functions, which we mentioned before, and which turned out to be equivalent to the Turing computable functions, which captures exactly that, the way we built up functions algebraically never takes us out of the computable functions. In order now to expose a specific undecidable set, we have to carry this approach, this counting approach to Turing machines, a little bit further. We have seen that there are only countably many Turing machines, but what we want to do now is actually number them. That means assign every Turing machine a number, M0, M1, M2, so that this list exhausts and lists all Turing machines. And in order to do that, we have to code instructions, the instructions of a Turing machine, because that's what completely determines the Turing machine. So what we want to do is take an instruction and code it as a natural number. To make our life a little bit more easy, we assume that Q, so the set of states, is always given as an initial segment of the natural numbers 0 to m, where this is the halting state. Furthermore, we know that x and y are always either 0 or 1, and we also represent the direction d as a number. So for d, we say that left is 0, right is 1, and stay, which we don't really need, is 2. Then we can define the code number of an instruction as follows. We take 3 to the p plus 1 times 5 to the x plus 1 times 7 to the y plus 1 times 11 to the d plus 1 times 13 to the q plus 1. So what we do is we take the first 5 odd prime numbers and raise them to powers that are determined by our instruction. And the reason for adding 1 here is that we want to avoid raising a prime to a power 0, which then would result in this term to be 1, and hence spoil kind of the decoding feature that is given to us by the uniqueness of the prime decomposition. So here's again the code of the code number of an instruction I. And by the uniqueness of the prime decomposition, each I is assigned a unique code number code of I n in the natural numbers. So to collect these codes of a single instruction together to form the code for a Turing machine, which is a finite list of instructions, let's assume I1 up to IK, we now do the same thing with the codes. So we say that the code of M is given as 2 to the code of I1 times 3 to the code of I2 times and so on, and then we have pk to the code of ik, where pk is the kth prime. Note that by our definition of the code numbers for instructions, those are always greater than or equal to 1, so here we don't need to add 1 in the exponents. So here we have the code number of the machine. It's just the code, a code of codes, so to say, coding each code into one big code. And this is called the Gödel number. After code Gödel, the Gödel number of M. So our coding function maps Turing machines to natural numbers. The way we defined it, it's not onto, right? Because we only assume certain values here, right? But it should be clear that we can easily modify this function to make it onto, so that every natural number is actually the code of a Turing machine. But once again, what we defined in this way, so the code of codes, so the codes of the instructions, put together in one big code, is the Gödel number of the Turing machine M, and often this is also called, or the index of M. Now you will probably ask, why are we going through such great pains to define a numbering of the Turing machines? We know it's a countable set, so can't we just fix any numbering, M0, M1, M2, and so on? Well, the reason for this is that the Gödel numbering, the way we define our numbering of Turing machines, is actually effective. What does this actually mean for the numbering to be effective? Well, that this bracket denote this function here of x and y. X and y are natural numbers, and it's not hard to see that this is a bijection from the set of pairs of natural numbers onto a set of natural numbers. So this is also called a pairing function. And we can use this pairing function to code pairs of natural numbers as single natural numbers. So it's similar to what we did before with the prime number coding, only here the number of numbers entering the coding, so the pairing, is fixed, namely 2, right? The effectiveness of the Gödel numbering is now captured or expressed in the following theorem. There exists a Turing machine U, the universal Turing machine, such that on input EW, so remember that's a single number, and every number represents a pair, such that on input E, W, U simulates the eth Turing machine on input W. So this symbol here means the following. So U halts on input W if and only if ME halts on input W. And if this is the case, then U outputs the same number that ME outputs on input W. So Again, this means that U is able to simulate the Turing machine ME on input W. And in fact, U is able to simulate every other machine on any possible input. That's why it's called the universal machine, because it can simulate every other machine. And in order to do this, for this to be possible, the encoding must be effective in the sense that the universal machine, looking at its input as an encoded pair, well, it will first decode this pair, look at the first component. Well, this will be an index of a Turing machine. So it has to now kind of recover the Turing machine from the index. And this is effectively or algorithmically possible through a Turing machine because, well, the way we coded this was carefully done and is in fact a computable function, passing from a list of inputs to the index of a Turing machine. We should add a little bit of notation here that we will use in the future. So when we say that ME on W down arrow means that it halts, ME halts on input W, and ME W up arrow means that ME does not halt on input W. The universal Turing machine will be very important later on, especially when we define, for us, when we define Kolmogorov complexity. So keep this in mind. There is a Turing machine that can simulate all other Turing machines. And this brings us to the halting problem. Informally, the halting problem is the question whether we can effectively decide whether a Turing machine, a given Turing machine ME, halts on an input or not. Right? So you're confronted with this problem many times while working with a computer. So if it enters a computation or a loop, and you, for instance, the spin hourglass or the spinning ball appears, can you tell whether the computer will actually return to a normal or an input state, or did it just crash? Will it do you have to reboot because it will never return to a normal input state? But for us, effective decidability now means computability through Turing machines. So what this question actually is, well, can we decide this question via a Turing machine? Does there exist a Turing machine M such that on input, if I give as input the Turing machine, the index of a Turing machine, and the input I want to run it on returns 1 if the eth machine halts on input W, or 0 if the eth machine on input W does not halt. Yet another way to put it would be to ask, is the set K, which consists of all natural numbers, or pairs of numbers, as codes, such that the eth machine on input W halts, is this set decidable? And this set K is called the halting problem, halting set or halting problem. It is the tradition to denote this set by K. It will later also denote a variant of Kolmogorov complexity. So that might be a little bit confusing, but it should always be clear from the context which set or which function we denote, whether it's the halting problem or Kolmogorov complexity. In the next lecture, the final lecture of this lesson, we will then show that the halting problem K is indeed an undecidable set. So this gives us the first example of a set that we can explicitly define that is also undecidable.